All right, in this lesson we're going to go through valence electrons and ionic compounds. So let's start with valence electrons. Valence electrons are known as outer shell electrons. So let's just do a quick Bohr diagram here. So we've got two core electrons here, and then any electrons that are not part of that core would be considered valence electrons. So if you think about an atom kind of like an onion, the outermost shell is where those valence electrons exist. Okay, those are only the s and p orbitals. The likelihood that two elements will form a chemical bond is determined by the interaction between valence electrons. We get to Lewis diagrams and you see how the electrons are shared. This will come back into play here. So let's look at the periodic table. So since we know that it's only the s and p, we can determine the number of valence electrons by the group. Okay, so this first one here would have one valence electron and then two valence electrons. We're going to skip all of our transition metals, so disregard the numbering there. 13, let me just cross all these out so we don't get confused. 13 would be 3, and then 4, 5, 6, 7, 8. Okay, and then 8, remember, are where our noble gases are. Okay, noble gases have a full outer shell. Everybody wants to be like the noble gases. Okay, so ion charges, elements in the same column tend to form analogous compounds. Typical charges of atoms in ionic compounds are determined by their location on the periodic table and the number of valence electrons. Okay, so let's go back to the periodic table. And again, the key here is the noble gases. Okay, everybody wants to have a full outer shell and have 8 valence electrons. Okay, so my first group has 1 valence electron. It's going to lose that outer shell to get to a completely full shell underneath. So let me show you what I mean. So I'm going to do 3 rings here. It's a little lopsided, okay? So we got 1, 2, 3, 4, 5, 6, 7, 8. Okay, so let's say I'm a group 1 metal. I only have 1 valence electron. So it's easier for me to get rid of that outer shell, that 1 valence electron, because it exposes a completely full outer shell below that. So when I lose an electron, I end up with a charge of +1. Group 2, same thing, but it has 2 valence electrons. It's going to lose both of those, and it will end up with the charge of +2. Anything in group 3 over here, or rather 13 on this periodic table, when it loses 3, it'll have a charge of +3. 14, our group with carbon in it, has 4. So it can either gain or lose, but you're not usually going to see that. So we'll disregard that column there. Okay, here's where it gets a little tricky. So our group with nitrogen, group 15, has 5 valence electrons. Okay, so it's really easy, or I should say it's easier for it to pick up 3 more electrons to get to 8 than to lose those. So because it's gaining 3 electrons, it'll have a charge of -3. Our group with oxygen has 6 valence electrons. It needs 2 to get to 8. So by gaining 2, it'll have a charge of -2. And then this one has 7. It needs to gain 1 to get to 8. Our noble gases already have 8. So you will not see those gaining or losing electrons because they have a perfect octet. All right. So here's an example. It says, what compound would form between sodium and mystery element X? Sodium has a charge of +1, and mystery element X has a charge of -1. They're both magnitude 1. They'll cancel each other out. So we'll end up with Na and X. That would be our compound. Okay, +1, -1. It forms a perfect compound where it's neutral. Okay, here's a different one. We have calcium with a +2 charge and mystery element X with a -1 charge. So I have +2 and -1. So I'm going to need 2 of these -1s to cancel this out. Ca has a +2 charge. X has a -1. Again, we had to do 2 of those to get everything to cancel out. So that would be our compound there. And that's it.